I'd like to go over one more time the problem that we did today in class. It has some unique features, as I pointed out. The unique features are that in this problem we have two samples, and we're trying to find out whether or not the difference between these two samples could be related to chance, or whether something statistically significant is taking place here. I'm going over this one because it is a little different, but as I pointed out today in class, it shares common features with all of the problems that we're doing in Chapter 6, 7, 8, and then again in 9. The basic problem is very similar. It's just a question of knowing which formula to use and how to set the problem up. So that's what I want to spend some time with. The problem comes right out of the book. It's the problem at the beginning of Chapter 8, Section 4. That's 8.4. You'll see it, the problem that has to do with this, this hypothesis that people who drive luxury cars, people who drive fancy cars, are more likely to be rude to pedestrians than people who drive less fancy cars. Okay, so let's start the problem by drawing out or laying out here in a table what's given in the problem. We have P1 as the proportion of people who are driving plain cars who are rude, and P2 the proportion of people in luxury cars who are rude. And the problem tells us that they were able to sample 33 people who were driving plain cars and 119 people who are driving luxury cars. And you can see again in this column over here that the number of people that they observed rude in plain cars were 8, and the number of people who were driving luxury cars who they observed behaving rudely was 45. So we can compute the proportion, which of course is what we'll need to do. So that's 8 over 33 in this case, and that works out to 0.242 if you do the division, and the number of people in luxury cars works out to 45 over 119, which equals 3.78. The proportion is 3.78. All right, so that's the beginning of the problem. Now let's lay out our hypotheses. We're going to start off with this null hypothesis over here, that in fact the kind of car that you drive has nothing to do with how rude you are. That's the null hypothesis. The kind of car that you drive has nothing to do with how rude you are. The alternative hypothesis, H1, is that the proportion of people who drive plain cars and who are rude is smaller than the proportion of people who drive luxury cars who are rude. As I shared this morning with you folks, I certainly find that the bigger, fancier cars when I'm out there on my motorcycle tend to be a lot more obnoxious than the little putt-putt Toyota Corollas that you see. But that's another story. Okay, so how do we get started with this problem? All right, well, we have our proportions over here. We need those. And first thing we need to do, well, not the first thing we need to do, but we're headed towards a z-score. We're headed towards computing a z-score. We're looking here to compute our critical value for z. So we're going to subtract, as we do with any z-score, these two values, P1 minus P2, and divide by the standard error. Now, in other problems that we've done, we were not comparing the values for two samples, but we were comparing the value for a sample statistic and a population parameter. We've got to scratch that out in this case because P2 is not a population parameter. It is the value from the other sample. So bear that in mind. Right, so what do we need here? We have this part. We have P1 and P2. Those are over here, right? We have P1 and P2. Those are over there. We can do that subtraction very simply. What we do need, though, is we need that standard deviation or standard error. So to figure that out, we're going to use the following formula. We are going to use P hat times 1 minus p hat times 1 over the sample size for P1. I'm just going to put P1 down there, plus 1 over the sample size for P2. And as always, we're going to take the square root of that. All right, not so bad, except for one thing. What the heck is P hat? I've got P1 and P2, but what is P hat? Well, in this kind of problem, we have to pool this. We have to pool these two proportions into one proportion. So we need to first compute before we can do this thing over here. Before we can do this thing over here, we need to pool these proportions. Now, how do we do that? Well, the formula for the pooled proportion is, again, given in the book. Sorry, that should be a little hat, not an N. The formula for that is going to be the value, the number of successes, and in this case, successful observations of someone being rude. It sort of is a little weird. Number of successes for 1 plus the number of successes, number of times people are rude if they're driving luxury cars, successes sub 2, over the sample size 1 plus the sample size of 2. All right, so now we're in business because we have this value over here. This value is 8, right? 8. We have the number of successes, number of times people are rude. That is 45. And we have the sample size, 33. 33 plus 119. And if you do that little bit of arithmetic, you are going to come out with 0.3487. I'll round it off like that. It's actually something a little different than that. We'll round it off like that. All right, so we now have p hat. With p hat, we can now figure out the sample standard deviation, or rather the pooled standard deviation. So let's do that bit of math. That is going to be 0.3487 times 1 minus 0.3487 times 1 over 33 plus 1 over 119. And remember, I said in class today, you really have to pay attention to these parentheses because you can make a mistake in something as simple as the order of operations in an algebraic expression, and you're going to get into all kinds of trouble. You're not going to get it right. You may understand it conceptually, you may have set the problem up properly, but if you make a computational error, you're simply going to get it wrong. And let's not forget here the square root. And this, after a lot of arithmetic, is going to come out to 0.0938. So now we are almost home. We are almost home. We can just about figure out our z-score. We've got our z up here. Let's move it down here. Z equals, what's that proportion again? 242.242 minus 0.378 divided by 0.0938, and that is going to come out to negative 1.45. So that is our critical value right there. That is our critical value. Now, let's draw this out in a curve, in our standard normal curve. So here we go. And we'll draw it out. And we know here that this is a z-score, right? This is a z-score over here. We know that the mean of any z-distribution is 0. And z-distribution is measured in units of standard deviation. That's not quite accurately drawn, but it's good enough. And then we have the empirical rule to pay attention to now. Okay? Now we're interested, as we usually are in any kind of social science or even physical sciences problem. We are interested in finding out whether or not these differences now expressed in standard deviation terms, these differences are due to, what's the probability that these are due to chance? What's the probability that these are due to chance? Typically, as you know, we want to be at least we want to have an alpha level. Okay, we want to be, oops, let me draw that alpha properly. We want to have less than a 5% chance, that the difference we observe, that the values that we observe are not due to chance, right? These differences could be because there actually is a difference between how drivers of one kind of car behave versus how another kind of car behave, or it could just simply be that one sample, was a little off, or both samples were a little off, all right? So remember your empirical rule. One standard deviation from the mean accounts for 68% of the area underneath that normal curve. One standard deviation underneath that normal curve, 68%. We are at about here, right? We're about here with this value. This value of z over here, that's going to put us just about there if I'm drawing that correctly. Let me make a little arrow there. Z equals negative 1.45, right about there. All right, we want to be 95% certain. That's just the reciprocal of 5%. We want to be 98% or 95% certain that this value here is not due to chance, that negative 1.45, that difference is not simply due to chance. Again, think of the empirical rule. The empirical rule is going to tell us that 95% of the variation is between two standard deviations either side of the mean. 95%. All right? Color that in there. Should have used a different highlighter. Apologies. Oh, there we go. That's how to do it. Okay? All right. Anything in this area over here, any z value that falls somewhere along over here, there's less than a 5% chance. There's a 5% chance or less, rather, that the difference that we observe is due to chance. The difference we observe here is due to chance. But where is our z value? Our z value is over here. All right? So it is to the right of the critical value. It is to the right of the critical value. Therefore, we do not have enough evidence to reject the null hypothesis. We temporarily, until we do another study, maybe we define rudeness differently, maybe we did not have, maybe the cars were not defined the right way, I don't know, could be anything. But for the time being, we are unable to reject the null hypothesis. And that's how you solve that kind of a problem. You can compute the exact probability here, and we did it in class, and I don't remember what it comes out to being, but if you take your calculator, and you absolutely must get a hold of this calculator. If you are doing this without this calculator that I showed you, you are not going to do well. You're just not going to do well. If you're sitting there looking up things in tables, that's just no way to do this kind of a problem. Does it work? Yes. Does it take forever? Yes. Does it help you understand how this stuff works? I don't think so. All right. So z distribution, always the mean is 0. The standard deviation is always 1. We would enter the critical value here. The critical value is negative 1.45, and it would spit out over here the probability. I don't remember what it was. I think it was something like 7%. I'm not sure, but you can check. And it's going to draw a nice graph for you as well. And that's a terrible graph that I drew. But it's going to draw a nice graph for you and show you what this area is. And finally, please pay attention to the video right before this one, because what you do with this little drop-down box here that you'll see when you actually open up the calculator, what you do with this little drop-down box here is going to be very important, because if you don't have this in the right way, you're going to get the wrong answer. You're going to get the wrong answer. So make sure you understand how to use that. And you know what? You can just play around with it. You can plug these numbers in and see what happens when you change that value. This is the correct answer. So see what happens when you change the value. All right, I hope that was helpful.